13.3, the fundamental theorem of line integrals, video 9. In the last example, we found the potential of a conservative vector field once we determined it was conservative by comparing the correct partial derivatives. And at the end, I casually mentioned, so if we were doing a line integral, we could just use the fundamental theorem of line integrals. But I thought it would be good to actually demonstrate what that means. So this is a continuation of example 3. You'll notice this is the same vector field that I had before. If vector function f of xy equals 3 plus 2xy I plus I squared minus 3y squared j, and c is the curve defined by r of t equals cosine of t I plus sine t of j on the interval 0 to 2 pi, let's evaluate the line integral over the curve c of f dot dr. Now, you might recognize this curve, especially if you watched the first video and the first series of videos, and this video titled Common Parametric Equations or Commonly Parametrized Curves. I forget the exact title. But this is a circle. It's a unit circle. It's not all of it. It's just the unit circle in quadrant 1 and 2. So it's the top half of the unit circle. No, I take that back. It's in quadrant 1. Pi over 2 is up there, so yeah. And let's evaluate this. Now, we could evaluate this the straightforward way, where we substitute everything in terms of t, and then we do a lot of antiderivatives, and we stick numbers in. But let's take advantage of the fact that we just showed that this was conservative, and there's its potential function, or rather one of its potential functions. The constant can be anything, so we'll just make it 0 in a moment. Since vector field f is conservative, with its potential function being that guy, 3x plus x squared y minus y cubed, and again, the constant can be anything, so we'll just make it 0. So in other words, the gradient of lowercase f is vector field f. Then the fundamental theorem of line integrals, Vitoli, says that the line integral of vector field f dot dr over the curve c is equal to the line integral over the same curve of the gradient of lowercase f dot dr, and here comes the fundamental theorem of line integrals. It says we can evaluate this by just evaluating f at the endpoints. So we're going to evaluate f at the point where t is equal to pi over 2 minus f evaluated at the point where t is equal to 0. Just like a regular definite integral, evaluated at the upper limit and evaluated at the lower limit. Now when I say evaluated, first we have to substitute the value of the parameter into our parametric function that defines the curve. So let's just talk this through. If I put pi over 2 into here, I get cosine of pi over 2, which is 0. If I put pi over 2 here, I get sine of pi over 2, which is 1. If I put 0 here, I get cosine of 0, which is 1. And if I put 0 here, I get sine of 0, which is 0. So now it's down to just algebra. I think we can talk this out. I plug in 0 for x and 1 for y. 0 for x kills these. Putting in 1 for y here gives us negative 1. So negative 1 minus, and if I do it the other way around, putting in 1 for x and 0 for y, putting in 0 for y kills all this, putting in 1 for x gives us 3. So negative 1 minus 3 is negative 4, and the line integral is over. Again, we could have substituted cosine of t and sine of t in for every x and y, cram that in here, dotted it with dr, so we would have to take the derivative of this and find the dot product of this with cosine and sine substituted in the right places, have a whole mess of trig functions waiting to be integrated, and eventually got into the same answer. So this is why being a conservative vector field is kind of cool. If you're a conservative vector field, and you know your conservative vector field's potential, then you can evaluate a line integral just like a regular integral. Antiderivative is that. Substitute and evaluate. Before we move on, I want to pose one more question that's going to be real easy to answer. I mentioned at the beginning of this problem that you may recognize this as a parameterization of the unit circle, but this is only the first quarter of it because it goes from 0 to pi over 2. But what if we took the whole circle? Don't worry, I'm not going to read you all of it, but think about it for a second. If our curve is defined all the way from 0 to 2 pi and it would generate the entire unit circle, what would this line integral equal? If you're actually doing any work, stop, because this is a thought problem, not a manual calculation problem. If we extend the interval so that the curve is the whole unit circle, then it is a closed curve. We already know that this is a conservative vector field. And the line integral over any closed curve of any conservative vector field is always 0. So sometimes it pays to think about, is there anything I can do to make this problem easier? Being conservative and being a closed curve makes the problem over because it's equal to 0. So here's another one to think about. We know that and I just want to try to get you thinking abstractly. We know that from here to here, the integral is equal to -4. We just got that. We know from here all the way to here, the integral is equal to 0. It's the integral of a conservative vector field over a closed curve. So what would it be if we went from pi over 2 to 2 pi? In other words, what would it be if we integrated the line integral over this portion of the unit circle? Think about it. We know the whole unit circle is the union of the black curve and the green curve. And we know that the integral over a whole curve is equal to the sum of the integral of its individual pieces. So in other words, the black integral plus the green integral would have to equal the blue integral. And so this would have to equal 4. Just thought I'd throw that out there. We're going to look at one more example of recovering a potential function in R3. That's going to be fun.